Forget propane tanks, power cords and fragile control panels. There was a time when entire households cooked, baked and heated their living space from a single charge of wood that lasted well beyond a day. In the 1700s, across Europe and early America, masonry, wall ovens and masonry heaters were engineered to trap heat so efficiently that one well-managed firing could radiate steady warmth and cooking temperatures for up to 40 hours. This was not primitive improvisation. It was applied physics, refined through centuries of trial and error. Today, as energy costs rise and grid reliability feels less certain, those same principles offer a serious solution. What you are about to learn is not nostalgia. It is thermal mass, controlled airflow, and combustion efficiency working together in a way modern kitchens rarely attempt. The secret lies in thermal mass and controlled combustion rather than constant fuel feeding. The defining principle behind these ancient ovens is thermal mass. Thick walls of clay, brick or stone absorb intense heat from a short fire and then release that heat slowly over time. Unlike a metal stove that cools quickly once the flame dies, a masonry structure stores energy in its mass. In the 1700s, builders understood that the fire had to burn fast and hot inside a contained chamber to transfer maximum heat into the surrounding masonry. The objective was not to keep feeding wood throughout the day. The objective was to saturate the structure with heat in one concentrated burn. Once the internal walls were fully heated, the embers were removed or sealed off, and the stored heat carried on for hours. This approach is dramatically more efficient than a thin-walled oven. It reduces fuel consumption and stabilizes cooking temperature. That is why a single, well-seasoned hardwood log, burned under the right conditions, can provide usable heat long after the visible flame is gone. The structure is built from earth, brick and intention. A high-performance wall oven begins with a foundation that can support weight. These ovens are heavy. Traditional builds rely on stone footings or reinforced slabs. On top of that base, fire brick or dense clay brick forms the combustion chamber. Around this inner core, layers of clay-sand mixture, often reinforced with straw, create thick, insulating walls. The clay mix matters. A common historical ratio is roughly 3 parts sand to 1 part clay, adjusted depending on local soil composition. The sand prevents cracking, while the clay binds the structure. Builders in the 1700s often tested mixtures by forming small bricks and allowing them to dry, checking for structural integrity before committing to full construction. For practical application today, start by constructing a compact combustion chamber size for your needs. A smaller chamber heats faster and uses less fuel. Line it with fire brick if available. Surround it with at least 4 to 6 inches of dense masonry material to build thermal mass. More mass equals longer heat retention. The internal flue path determines whether heat escapes or stays trapped. The physics that set these ovens apart lies in the flue design. Instead of allowing hot gases to rush directly up a chimney, historic builders routed smoke through a series of internal channels before exiting. This forced the heat to transfer into the masonry walls before leaving the structure. In many masonry heater designs, the smoke path snakes horizontally and vertically within the body of the oven. Each turn extracts more heat. By the time exhaust reaches the chimney, much of its thermal energy has been absorbed. To apply this principle on a smaller scale, create at least one directional change in the flue path inside the structure. Ensure passages are smooth and properly sized to prevent smoke backup. A good draft is essential. The balance is simple but critical. Slow the heat long enough to capture it, but not so much that airflow collapses. The firing method determines whether you get 40 hours or, well, just 4. Performance really depends on how the oven is fired. A single intense burn works better than a slow, smouldering fire, you know. Always use dry hardwood. Open the airflow fully at the start to allow rapid combustion. The interior should reach a high temperature quickly. In traditional masonry ovens, builders waited until soot burned off the inner dome, leaving the brick surface clean and light in colour. That visual cue indicated sufficient heat saturation. Once the structure is fully charged, rake out excess ash or coals if baking bread, or close the intake to reduce oxygen flow if the coals remain. Seal the oven door tightly. From that point forward, the oven radiates steady heat without additional fuel. In practical use, this means baking bread first at peak retained temperature. Several hours later, the oven remains hot enough for roasting meats or slow-cooking beans. Even the following morning, residual warmth can dry fruit or dehydrate herbs. This system supports both survival resilience and everyday utility. The strength of this design is not limited to crisis scenarios. A properly built masonry oven reduces wood consumption dramatically. It stabilizes cooking temperature without constant adjustment. It can also heat the adjacent living space in cold climates. For those interested in preparedness, this system removes dependence on gas lines and electrical grids. For homesteaders, it provides a multifunctional heat source that serves cooking, baking, and space heating in one structure. For history enthusiasts, it represents applied physics from the 1700s that still outperforms thin steel appliances in energy retention. One practical example is incorporating the oven into a shared interior wall. As heat radiates outward, it warms multiple rooms. Another is designing the top surface flat enough to function as a warming bench, a feature common in Scandinavian masonry heaters. The enduring lesson is that mass, airflow and patience outperform modern convenience. Technology often prioritizes speed and portability over efficiency. The ancient wall oven does the opposite. It invests energy up front and rewards you with long-term stability. The physics are straightforward. Maximize combustion efficiency, capture heat in dense material, and release it gradually. If you value old-world engineering, resilient design, and practical survival knowledge rooted in history, subscribe to the channel and share this episode with fellow enthusiasts. The most powerful solutions were built centuries ago, and they are still waiting to be used.